My name is Mick Whelan. I'm a reader in environmental science at the University of Leicester, and I sit on the coordination team for the UKRI Landscape Decisions Programme. In this plenary presentation, I'd like to try and summarise the presentations from the 12 talks in Theme 1 of this virtual networking event, entitled Comparing, Combining and Improving Models and Creating Tools and Frameworks. Before we put the presentations, I think it would be useful to set them into context. They're all part of the Landscape Decisions Programme, which was set up in recognition that landscapes are multifunctional entities which can deliver a range of benefits in addition to the agricultural commodities we traditionally think of as products of the landscape. These additional benefits include storing water and carbon and enhancing biodiversity. If we as a society want to maximise these benefits, then we need objective, evidence-based approaches to help us do that. Landscapes are complex, so that means we need models as frameworks to guide our decision making. All the projects which were presented in this theme sit in work packages 1 and 2 of the Landscape Decisions Programme, developing new mathematics and building new model solutions. Some of them describe large standalone projects like Advances in Agland, and some of them were awarded under relatively recent calls for smaller projects to develop new mathematics. This is a list of the presentations in this theme. All were concerned with modelling. Some were about generic modelling techniques, for example, the two presentations by Richard Everett on calibration. The presentation by Alex Hagen-Zanker looked at urban expansion using an agent-based approach. The presentation by Ben Marchant looked at uncertainty and scale issues in the context of improving BGS data product. And Paula Harrison's presentation was about building rule sets for land use dynamics using artificial intelligence. However, the remaining 7 presentations were specifically concerned with modelling natural capital and ecosystem services. Most models of ecosystem service provision take a set of characteristics describing physical landscape features such as topography, soil properties and climate, and a set of characteristics describing how that landscape is used, i.e. how it's partitioned, the nature of the field boundaries, the land cover, aspects of land management such as agrochemical inputs, and the presence and nature of specific interventions, for example, the allocation of land for wildflower meadows. And they calculate a set of metrics describing the ecosystem services which are generated by that combination of characteristics. This could be, for example, crop yields or meat production, but it could also be predictions of the water balance, which might have some benefit in reducing flood peaks, water quality, which might be affected by fertilizer or pesticide use, carbon sequestration in soils, air quality, biodiversity, which in turn can be related to functions like pollination, which can then feed back into enhanced crop yield, or some aspect of aesthetic value, or a metric describing the value of the landscape for recreation. Models can be used to make these calculations for the current set of landscape characteristics, but they can also usefully be used to make them for scenarios which describe the effect of intentional interventions or the possible responses of land use and land management to shifts in policy via subsidies or changes in climate. They can also be used to try and optimize how land is used and managed in order to maximize one or several benefits, taking into account the possible synergies and trade-offs involved. A nice example of the interaction between different services and an illustration of the need to include feedbacks in model calculations was given by Emma Gardner in her presentation. Increasing the area of land set aside from crop production on a farm will decrease the cropped area and hence perhaps decrease total yield, but will increase biodiversity and encourage pollinator activity. And this in turn may enhance the yield of the remaining crop both in the adjacent field and in neighbouring fields, so the net effect could be win-win. In principle, models are objective and hence should give consistent and reproducible outputs, but are they always robust? In other words, do they give good descriptions of the relationships between the inputs and the predicted outputs, which allow us to make good decisions? In this theme give a nice illustration of the range of models which exist or which are being developed in this program, which could help us make better landscape decisions. Some of these models have similar aims. Some are very specialized, i.e., they're focused on one particular aspect of ecosystem service provision, but some might be more general and yield several ecosystem service metrics, such as the 6 models described in Jessica Finan's presentation. How do these different models compare? This is being looked at by the Ensembles project and by the Aberdeen-led Land Allocation and Nature Valuation Comparison project. The model you choose needs to generate all the metrics required. If it doesn't, it may be possible to combine different models, taking into account the feedbacks between them, and this is what the Reading Group are trying to do in their project, which I've named Pollinators, Crops and People PCP. Some models are simple and some are more complex. There are pros and cons in both cases. Either way, the model employed needs to be fit for purpose. Sometimes simple models work just as well as more complicated ones and require fewer parameters or have lower runtimes. Some models are deterministic, i.e., a given set of inputs always produces the same set of outputs, but others are stochastic, i.e., some or all parameters have some random component, such that a distribution of outputs is generated rather than a single number or a single time series. Several of the presentations use stochastic concepts, including the approximate Bayesian computation approaches discussed by Richard Everett and Alex Hagen-Zanker, and the modified Markov decision process models described by Julia Brettschneider, and I also suspect the Advances project. Spatial and temporal scales are important model features. Some models are aspatial, while others are spatially explicit. If they're spatially explicit, then the scale at which input data is represented could affect model outcomes. This is being considered by Ben Marchant's project and by Emma Gardner's project. Spatially explicit models allow the location of landscape interventions to be identified, for example, specific areas for land use conversion, which means that scenarios can be more realistic. Several projects are also considering the timescales over which benefits from land use changes might be realized. This could be an important factor to take into consideration when comparing options within a decision-making context. For example, it would probably take longer to see benefits from a farm woodland than from establishing a wildflower field margin. If models are to be used in a decision-making context, it would be useful if stakeholders were able to run them for themselves, or at least the outputs need to be understood by stakeholders and be useful to them. This is specifically being investigated by the Aberdeen team, but was also mentioned by others, including Emma Gardner and Richard Pywell from CEH. Related to ease of use is data requirements. This is an important consideration. If the data are not available at the scale required, then it may not be possible to run the desired model, or the quality of the conclusions reached could be compromised. All models have parameters which control how inputs are converted to outputs. Sometimes parameters can be estimated independently, but often some sort of calibration is needed. There are several ways in which calibration can be performed, and this is being considered explicitly in the project described in Richard Everett's presentations and by Alex Hagen-Zanker. For more complex models, such as those which attempt to represent interacting biophysical processes mechanistically, but also for simpler models which make calculations for large geographical areas at high spatial resolution, model run times can be long, and this can limit the number of times calculations can be performed, or could limit model runs to very specialized, high-performing computing facilities. Sometimes it's possible to produce model emulators, also known as metamodels, of more complex models, and this is the topic of Anna Harper's presentation. The development of more efficient computational methods was also being considered by Ben Marchant's presentation. Related to calibration, but very different, is model validation. This is a test of model performance, usually by comparing model outputs against an independent dataset which was not used in the calibration process. Several of the presentations in this theme consider validation. Although none of them go into details, it's important to point out that there are several ways to do this, including some novel statistical approaches. Many of the presentations in the theme talked about uncertainty, and this is an extremely important aspect of modelling which has received variable attention in the past. All model outputs are uncertain, either because the structure adopted to describe the relationship between inputs and outputs is inappropriate, sometimes called epistemic uncertainty, or because the input data or parameters are uncertain, and this is sometimes called aleatory uncertainty. If models are to be used as a guide for decision making, it's important to estimate this uncertainty, and several of the projects in this session made an explicit attempt to do this. One aspect of model development which was not mentioned much in the presentations is sensitivity analysis. At its most simple level, this is the evaluation of the relative change in model output for a given incremental change in a parameter value, either one at a time or all together. This is important because it allows model users to spend more time getting good estimates for the parameters which matter and less time on parameters which don't have a big influence on the final predictions. Finally, although many models already exist for modeling ecosystem service provision, the existing array of off-the-shelf tools may not do everything you needed to do at the scale or temporal resolution you need. In this case, new models and new statistical tools need to be developed, and this is an important aspect of the Landscape Decisions program. In addition to the projects listed here, which describe new models, we also heard from Emma Gardner and Richard Everett about ways to link different models together to generate predictions of multiple benefits. Some aspects of the landscape are difficult to value quantitatively, labelled as hard to value assets by Andrew Lovett. This includes biodiversity, which is straightforward to measure, but perhaps more difficult to assign a value to for comparative purposes, except via associated services such as pollination. Other hard to value aspects of the landscape are its aesthetics, how it looks, and what this means to people who live in or visit it, and the cultural or heritage value of the landscape. These are important, and attempts are being made to explicitly include them alongside metrics which are easier to calculate, for example in Advances, the Reading project, and in Julia Brettschneider's project. To conclude, I'd like to end with a couple of quotes from the statistician George Box, who famously said, "All models are wrong, but some are useful." I think all modelers accept this aphorism, and many of the presentations in this theme are explicitly concerned with aspects of modelling connected with both establishing the extent to which our models are wrong in the process of calibration and validation, and in attempting to explicitly quantify uncertainty. They're also all concerned with making models useful for making landscape decisions. I've thoroughly enjoyed watching this selection of presentations. There is some really exciting and insightful work going on. On behalf of the Programme Coordination team, I'd like to thank all the speakers and their collaborators for taking the time to tell us about their projects. We look forward to seeing how they evolve and to meeting up with you all face to face in the not so distant future.